Okay, hi everybody. So in this lesson here, we're going to take a look at relations. We're going to introduce this idea of a relation here. And what a relation is it's, like it says right here, a relation between two sets is a collection of ordered pairs containing one object from each set here. Now remember that a set in and of itself here, okay, a set is a collection of objects. Now the definition is a little bit more precise than that. Okay, there's a little bit more to it than that. But anyway, a set is a collection of objects. Now, specifically for what we're interested in, we're looking at sets of numbers typically. Okay, let's just be honest here. It doesn't always have to be numbers, but usually we're talking about numbers here. So what we've got here is object X is from the first set, and then there's an object Y that's related to the second set, and we put them in a relationship like this, X comma Y. So really, what a relation is, when it kind of boils right down to it, is just a set, which is another collection, okay, a collection of ordered pairs. So for example, what you got right here, 1, 3, 2, 4, 3, 5, those 3 points together, that's a relation. And again, we're using the braces here to indicate a set, okay? It's just a little bit of notation. You don't have to be too worried about that kind of notation right now. But just that's typically what we would do with that, right? We would put the objects of a set inside our braces here. Wow, man, I really butchered that one. Hold on. Clean that one up a little bit. Yeah, so we put our objects inside those braces there to indicate a set here. We've got two different sets, one where we're going to grab the x coordinates from, one we're going to grab the y coordinates from. Now, there are a few different ways that we typically represent sets. Or sorry, relations, I should say. One is a table of values. Okay. A graph is another great way of representing a relation. Sometimes we can come up with a nice equation for relating the values from the different sets here, right? Where there is really a nice direct connection from x to get to y. Right? So in this case right here, for every x coordinate that we find, the y coordinate is going to be just 2 greater than that. Another way of setting up sets here, or representing sets, is by an arrow diagram. And by an arrow diagram, what we mean by that is this here. We've got our two sets here, okay? So here's our first set right here is in this little oval here, and our second set is here. So we're going to have some objects here. Let's say we've got let's just say like A, B, C, D. And then over here, we've got, I don't know, L, M, N, O, or whatever. And then what happens here is, to express the relation, what we do is we use little arrows. So we're going to say like A goes together with L. Let's say B goes together with M. I don't know, maybe C goes together with N. Sorry, M as well. And then D, well, D's this weird one here. D goes with both of those, right? So this is just one way of doing it, where we simply use arrows to represent that connection. So instead of like putting parentheses around, like here in the table of values, we have a connection here, right? I'm putting the parentheses around the points here. On the graph, it's really easy to see, because as soon as I indicate a point, I've indicated an ordered pair, some coordinates here. The equation, once again, basically what happens here is for the x, you're going to pick a value, and then I know that for the y, it's just going to be that value plus 2. Okay, so it's pretty easy to see the relationship here. So here we use the arrows. Okay, we use the arrows to indicate the connection here, or the connection or relation. Okay, it's with the arrows here that we're creating the ordered pairs. So you'd have this A comma L, B comma M. You also have C comma M, and then you'd have D comma N and D comma O. Okay. Now, some terminology that we need you to be comfortable with. And one thing that we need you to be comfortable with is these ideas of discrete and continuous data. Now, there's another thing I'm going to throw in there as well, but discrete and continuous. Now, there is a little bit of an error here. When it says all data values, and then here it uses specific integer values, I think we want to switch those, okay? Basically, with discrete values, we're using like integer values, and the data is counted. Okay, the values are counted. So, and on a graph, like it says right here, the points would not be connected on a if the data is discrete, we don't connect them. So what we're saying is stuff like shoe size, t-shirt color, the number of people in a classroom, objects that you can't cut into fractional pieces here. Okay, um, that's the sort of thing that we mean by discrete. Okay, so if for example we're I don't know, let's say we're talking about let's say the number of people, and then all of a sudden here we're saying like the cost of renting or the cost of tickets, let's say, or how much we've spent. You're going to have these little dots here. You wouldn't connect them because a connection would imply, for example, there's a fractional number of people there, and we don't have that. Okay, there's just a countable number of people. Now, compare that to continuous data, okay, in which case we're not talking about the integer values, we're talking about all values, okay, all the data values, and the data is typically measured, not so much counted as measured. Okay, so, and in this case right here, on the graph here, all the points would be connected. So for example, let's say you had time and the height of a tree. Okay, then you're probably, you'd have all points connected there because at any given time there, and like you can split that up between days, you can have fractional days, you can have, pi number of days or whatever, and you'll be able to find a height that corresponds to that. And so weight, temperature, height, those are all examples of variables that could be uh, continuous. Now, there is another one here, and I'm just going to throw this out here just because I am who I am here. There is also what you might call discontinuous data. Okay, and this is going to be data that is continuous. Whoops, is continuous. Oh, that looks terrible. I'm going to fix that there. Okay, is continuous, but with gaps. Okay, so just as an example of that, you might, for example, have time, and let's say this is the money in your bank account. So the way that would normally work here is, you've got money in your account here. It sits like this. It doesn't change. And then all of a sudden you add money to it. It jumps up to here. Then you take money out, add money in. So what you've got here is it is continuous where it's along those lines there. But then there's these jumps. There's these gaps, these little openings in the graph where there's these little holes there. There's other ways that can be set up too, but anyway, discontinuous data here. You don't really have to worry about that right now. I'm just throwing that out there. So now when you're constructing a graph, okay, when we're making these things here, some things that we want you to pay attention to, we would like you to include a title. Okay, and usually it's going to be the y-axis, okay, data versus the x-axis data. That's just typically how we would set that up here. We're going to have a grid, okay, some sort of a coordinate plane. Now, that doesn't always have to be, it doesn't always have to be a grid, although for what we're going to do, it's mostly going to be a grid. You're going to identify the range of the data that you're given. So, and that's going to help you build the scale, because really what's important here is we need to be able to read the data on your graph, and having a good scale, a clear scale there is a huge part of that. So then we're going to have the data on the x-axis is going to be labeled, okay, with the name of the variable and the units. Same thing with the vertical axis, labeled and with the units represented. Okay, so that all said, let's now take a look at a couple of examples. So here the question says, Draw a graph for each of the scenarios below. Be sure to include the essential features and determine whether the data is discrete or continuous. Okay, so let's just slide that up here so we can see the graph. So Tina, so this is the first one here, example A. Oops. Moving stuff and it's not moving here. So Tina recorded the revenue for tickets sales for the school dance. Her data is shown below here. Okay, so what we want to do here is, first of all, we want to figure out, well, what determines what? Okay, in other words, what's going to go on what axis here? Is the number of tickets determine the revenue? Does revenue determine the number of tickets? And I think most of the time the relationship kind of goes this way. Okay, the number of tickets that we sell is going to determine the revenue that we get here. So we're going to put number of tickets here on the x-axis, and we'll put revenue on the y-axis. Now, just so that everybody is aware of this, because I know that sometimes as we go through this, people aren't aware. Revenue is the amount of money that comes in. It's not profit. With profit, you have to get rid of your expenses here. Revenue is just the amount of money that's come in here. So this is the title for this would likely be revenue versus tickets, or the number of tickets. Okay, that's typically how we would do that. And then on our scale here, I'm just going to follow what I'm seeing on the table of values. So this would be like 5, 10, 15, 20. And I might do the same thing on the y-axis here, 10, 20, 30, 40. And now I'm going to plot my points. So, and remember that on a table of values, your rows tend to be your points, your ordered pairs here. So 5, 10, 10, 20, 15, 30, 20, 40. Now, here's the thing. Would we connect those points? Well, no, because you can't sell a fraction of a ticket. So instead, what would typically happen here, and I'll maybe change colors with this one, is there would be, for example, 4 other points that would show up in between. 4 other points that would show up in between for each number of tickets. So for 11 tickets, 12, 13, 14, and then we got the 15, and then you got 16, 17, 18, 19, and then you've got the 20 here. But those wouldn't be connected. That's about the best that we would do. Now let's compare that to this next one here. The next one says that Jerry recorded the temperature outside every hour over a 4-hour period starting at 7 a.m. and the results are shown below. Okay, so now actually I am going to have to move this up just a little bit to get underneath here. So which one depends on what? Does time depend on temperature, or temperature depend on time? Well, I think it's pretty clear. Time just kind of barrels ahead, doesn't really matter. So temperature is going to depend on time. So we're going to put time down here, and we'll put temperature over here, and we'll put degrees Celsius. Now for time, time's not really going to start at 0. We're going to start at 7 a.m. here. So I'm going to put a little break in the graph right there, and then we'll put a 7 there, and then 8, 9, and 10. And then on our temperature side here, notice that it's not going up by a nice steady amount here. So I don't know, I might just do this. I might just go 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, and then just write it out by twos. 2 degrees, 4 degrees, 6 degrees, 8 degrees, 10 degrees, and then 12 degrees. And then again, just like we saw, oh, sorry, and then the name of the graph, I've got to name the graph here. This is going to be temperature, whoops, versus time. Then I'll plot my points. Okay, so 7, 5, 8, 7. It's going to be about there. 9, 10 goes up to here. And then 10, 11, slightly more. Okay, now in this particular case, would the dots be connected? Does it make sense to think about like a fraction of an hour like a fraction of a degree Celsius? And the answer is yeah, it does. So it would make sense to kind of put a line to go through those. So as a result, because of that little bit right here, I know that my data here in this first type here is going to be discrete, whereas this type of data here would be continuous. Here, fractions don't make sense because we wouldn't sell a 25% of a ticket. But over here, does it make sense to talk about like 25% of an hour? Well, yeah, I mean, it's a little awkward. You don't normally do it that way, but yeah, you could totally do that. Okay, now we're going to talk about a little bit more terminology here. I want to talk about the independent variable and the dependent variable. Okay, so and by this time we've already sort of pushed in that right direction here. So the variable whose values are not altered by changes in another variable. Okay, now I'm just going to put a little star here. That is not necessarily true the way that's stated here. Okay, because we can, in certain situations, whoops, sorry. I was gonna write something different there. In certain situations, change which is considered independent or dependent. Okay, so to say that there is a variable that is not altered by changes in the others, well, we're saying that to give you this idea that the independent variable is the one that you have control over. Okay, if you're to compare this to like a science class here, this is your manipulated variable. Now, in most cases that you're going to look at here, this statement here is going to be true. It's not altered by changes in another variable. But there are circumstances here where it's not hard to see how that situation could be swapped. And so sometimes we're making a choice as to which one is manipulated, which one is the responding, if you will. But in either case here, regardless, this is always going to be represented on, okay, the x-axis, always represented on the x-axis. So that's once I put something on the x-axis, I have decided that that's going to be the independent variable. Another way of thinking about it, everybody, is that this is the input value. Okay. Now, the dependent variable is the one whose values depend on the values of the independent variable, and that's true. That is the way that is going to work here. Okay, that's totally the way that's going to work here. Now, could that be changed in certain circumstances? Yep, kind of depending on the nature of the relationship. But we typically consider this to be the responding variable. Okay, so I make a change to the manipulated or independent variable, and then I watch to see what happens to the dependent variable. Now, we put this one on the vertical axis, is on the y-axis, okay? Always on the y-axis. So that when I see that somebody has made a choice and has labeled the y-axis in a certain way, I know that a choice has been made as to what the dependent variable is, okay? The manipulated variable, okay, always comes first in an ordered pair, and the dependent variable always comes second in an ordered pair. Okay, so your ordered pair. Oops, sorry, I don't want to do that anymore. I want to do the pen. The ordered pair is always going to be independent variable, comma, dependent variable. Okay, and typically for us, that's going to be x, comma, y. And we consider that to be the dependent variable, if you want. We're going to consider that to be like the output. Okay, input versus the output here. And so, how do we identify the independent versus dependent variables? Well, okay, typically, well, sorry, with the ordered pairs, this is not, I don't want to say typically because that implies that maybe sometimes it doesn't. But this is the way that works here. Independent, comma, dependent. For a table of values, typically the independent comes first and then the dependent comes second. in an equation, the x is typically the independent here, and usually the expression is written like this, where y is equal to, and then something going on to x. So what happens here is I choose my x value, and then by doing a little bit of work, I create the y value. So I choose, okay, I choose x and do some work. Whoops. Okay, and do some work to get y. That's why y is dependent. And then on a graph, this is very similar to that ordered pair. The independent is down here on the x-axis. The dependent value is up there. That's, once you see it like that, that's, you're communicating that that is the independent variable and then that's the dependent variable. Okay, let's take a look at some more examples. So for this question, we're simply asked to identify the different bits of information here. So we've got student and height here. So now, based on what we had just said a couple moments ago here, the dependent variable is very likely going to be over here, right in the second column here, whereas the independent variable would be right here. And actually, that makes sense. Okay, the height of someone depends on who it is. Okay. Measuring someone doesn't determine who they are. Okay, it's the other way around here. So the dependent variable would be height, and the independent variable would be the student. Now, as a result of the type of data that we're working with, now think about this, is discrete or continuous? Well, it can't be continuous because is there any kind of fractional partial way of going from Amber to Charlie? Like, does one person kind of morph into the other? And the answer is no. These are distinct individuals, okay? There's no fractional students here. So this is discrete. Okay. Now, oddly enough, in certain circumstances, that is a little bit more difficult to figure out whether it's considered discrete or continuous. But here I think it's pretty clear that that's the way that one's got to be. Okay, so now just for a moment, we want to illustrate for you guys the types of the rate of change that you can get in the graphs here. So we're talking about continuous data, okay? And we want to have you aware of the different sorts of graphs you can have. Now, there's like an infinite number of types of graphs you can have, but some of the basic ones that we're going to be looking at here. So, for example, what does it look like if something illustrates or has a constant increase? Well, it's just going to look like something like this. Okay, so notice that it's a straight line, but it increases as you go left to right here. Whereas a constant decrease is going to look, whoops, oh boy, that's not a very straight line. Hold on, let's try that again. Constant decrease is going to look something like this. Okay, straight line, but it drops as you read to the left to right here. Because remember, graphs are read left to right. Okay, so gradual increase means it's going to start low and it's going to increase, but it's not going to do it as a straight line. It's going to do more and more and more and more. It's gradually increasing more and more and more. At least that's the intention here. Gradual decrease would be something that starts kind of high and drops down, and then it decreases. It's constantly decreasing, but at a smaller amount here. This next one here is a gradual increase followed by a decrease. So that's going to go up and then drop back down again. And then clearly we can have a graph that does something different that can go down and then back up again. And then no change, kind of no movement here. Basically, we're locked at a certain spot here and we stay there. So it's just a horizontal line here, okay? So with that, let's take a look at a question or two that asks us to kind of grab one of those. So this question says, choose the correct type of rate of change for the graphs, or choose the correct rate of change graph for the following scenarios. Okay, so hot chocolate cooling over a period of time. Well, let's think about how that works here. Does it cool at a constant rate? And I mean, maybe you've never really thought about it before, but actually what happens is when it's quite warm, okay, it cools quicker, and the closer it gets to kind of room temperature, the slower it drops here. So this is actually going to be a gradual decrease. Now, how about the position of a football being thrown by a quarterback to a catcher? Now, okay, now think about that. That's going to go up and then back down again. Okay, so this is going to be a gradual increase, / decrease. And you might even question the word gradual there because it happens pretty quick. Firefighters climbing up a ladder, resting on a burning building. Okay, well, that is a constant increase, right? They are moving up that ladder at a constant rate typically. Okay, just going like up like that. How about watching a movie on Netflix at home over time? Now you might wonder, well, what on earth are we talking about here? Well, the intention here is no change. Basically, you are not moving. You're just sitting there watching TV. So yeah, no movement. Everything kind of stays constant. So you're just sitting there over time in the same position, not going anywhere. So I hope this gives you just a little bit more knowledge about relations and how we talk about relations.